I would like to start with a short quiz. Who knows what this is? If you know the answer, shout it out loud. Do not raise your hand. Any choices? I can't hear. Three-letter acronym. Who is the righteous? Good. Okay, so now I'll give you some TLAs, three-letter acronyms, and you will try to shout it out loud if you know the answer. Oh my God, oh my goodness, if God is too short for you. IoT, Internet of Things, good. DOS, DOS. Pardon? Denial of service. What about disk operating systems? So actually, TLA can have multiple choices, right? And indeed, yes. And also TLA, by the way, it's TLA, right? SVM. Well, I guess that everyone here knows what SVM is. Support vector machine, a machine learning classifier from the analytics domain. And finally, SDN. Indeed, good. Software-defined networking. I will shortly say a couple of words about SDN. Just to note that it's a branch of the broader term SD something, which can be protection, such as SDP, or storage, SDS. Now, software-defined applications and infrastructure, what stands for SDX, as well as analytics, of course, needless to say it here, two out of the top 10 leading technology trends for the current year by Gartner. For this was expected in the last year. And the research that I'm going to present now is focused in these two domains. So it quite well motivates the research. So what is SDN? Essentially, SDN is an approach in networking that separates the control on the network from the network itself. And this gives a much more flexibility because it's a holistic view of the control and the management of the network. And this flexibility gives a dynamic possibility to put together more sophisticated applications in a much more instant fashion. An example of such an application that I will focus in this talk is a load balancer. So if you look at the network, it produces some data. We gather the data, and we send it to this application. Now, this application essentially is a decision-making application. Okay, it receives some data and output decisions. It sends the decisions to the network, to the controller, this brain. It's the same brain, by the way, that we saw just before for Robert's talk. It's kind of spooky, isn't it? Now, example of this input data that goes to the application can be from the network, can be frame delay or latency, or changes in the latency, what is called jitter in the networking jargon, packet loss, and so on. And we monitor this data, and the application responds to it and sends it to the controller to induce it to the network. Let's see an illustration. Here you see in the right-hand side a client that watches some video stream from a remote server. And from their perspective, they are connected. The data is the green line that you see. And now I will run the simulation, and you will see a simulated disruption in the link that it's working now, the yellow one. And this disruption causes to the application to do something, to respond to it, and to reroute the connection. So this is very trivial. In SDN, compared to where you don't have the approach of SDN, where it is not trivial to do it. I will show you now a real demo of such a system. It is called the one virtualization system. What you're going to see is a video, a promo of The Simpsons, very short one. And in the right-hand side, you will see in the bottom a control system for the demonstrator, where you can put deliberately some disruptions into the system to increase the latency or to increase the packet loss and so on. And on the in the upper side of the right-hand side, you will see it's quite easy, not easy to see because the screen is. Anyway, the green lines are the routes through which the data goes. Now I will run the movie, and you will see that what happens. Now the demonstrator increases the latency on route number 1 and also on route number 2, and you see that the application, the load balancer, switches between the routes in order to keep the moving ongoing. And in a regular system, you just have to wait or to re-download the movie. So this system responds quite well to disruptions in the lines. However, bear in mind that this system is responsive. Namely, it monitors the data, and it responds if it sees the disruptions. So I want to emphasize the differences between being reactive to being proactive. And this is the gap in which this research now, this hybrid model that I'm going to propose, is bridging. What I claim now is that being reactive is not different of being proactive, because if you think of it, let me mention what you already know but you forgot. We always do predictions. Even if we respond to some things, we make predictions that those things just have no change. The state doesn't change. If we would use a different approach rather than responding, so the result might be different, as in this picture. Let's see, regarding our system, what it means. So here I have again the monitoring system and the engine of the application that observes the data. The brain, the SDN controller, is over there, and this is the switch, virtual switch, through which the data flows. Now I will run the simulation, and you will see a packet goes in. It is registered in the engine, and it goes through link number 4. Now there's a failure. The engine responds to this failure, and it reroutes it to link number 1. The same scenario now, where I put a predictive model, forecasting time series forecasting model. Sorry. It learns the data from the time series and sends to the engine predictions. So we want to chase or to be in front of the failure. And this is how it goes. Again, the same scenario, the packet goes through link number 4, then the engine decides to reroute to link number 1, and then the failure occurs. Okay, so this is where we want to achieve the goal. Okay, so now let's see what it means in terms of time series forecasting. So what do we do in time series forecasting? We have a time-dependent variable, and we want to predict what is the next tick, the next very tick. So we use some models like linear regression or other pattern-based models. It can be moving average, there's RIMA models, and so on. And by the way, also the reactive is a model. It is called naive model because it says what the weather of today is going to be the weather of tomorrow. And it is quite strong model, by the way. It is quite predictive, a strong predictive model in time series, at least for the short-term prediction. And then we have the actual value that surprises us sometimes, and we want to catch it. And another thing is that we don't only want to predict the data very accurately in terms of the distance from the data itself, from the value itself. We want to make classification. So we use short-term prediction, we use long-term prediction, and we also use classification. So if, for example, the load balancer decides to reroute if the latency exceeds some threshold value of 150 milliseconds, so we can binarize this value. We say above 150 milliseconds you reroute, otherwise you stay like this. So this is a simple rule for the load balancer. And we test our system, our forecasting model, using classification evaluation, such as recall, precision, and so on. So this is I presume that it is familiar to you, the evaluation metrics of classifications. So what do we require from the model? We want the model, the forecasting model, to be adaptive because networking data is very, is not stable. I would put it like this. And the adaptiveness, I mean that for the same type of data, it can change within time. So we want the model to be adaptive to it and not to have underlying assumptions or underlying approach like, I don't know, regression or other models. We want it, of course, to be fully automated, so we don't need to have a human to tune the parameters. We want it to be robust. Robustness is a very important property in this field because we don't want the model, if it is not the best model all the times, at least we want it not to be the worst or not to be, you know, in a very poor situation. So if it is the runner-up, it's okay. If it is the third place, it's still okay, but not worse than that. And of course, easy to use is quite trivial. So this is the model that we proposed. Actually, it is an ensemble of time series forecasting models. So we plug in the common time series forecasting models like moving average, moving median, regression, ARIMA model, whatever you like, you can plug in, plug out. And we just use it as a perceptron, as a weighted average to calculate the output. But also, we do some competition between the models. So we tune constantly the weights of the models that have, in the recent time, the least error. They gain the higher weight. And we also optimize the parameters of each model in an agnostic fashion. So we do not care how many parameters do you have and what they mean. We just apply some optimization algorithm. For example, it can be genetic algorithms or so, but it is not. I just give an example. And this competition makes each model to have its best performance, and then the output of the hybrid model follows these performances. So let's see some experimental results, and I'm going to follow what the professor said in the morning to show that my curve is better than yours. So this is basically what you're going to see. So this is the list of the algorithms that we plugged into the model. We use 4 data sets, as I mentioned before, networking data sets, and also a synthetic data set taken from the UCI repository. We use short-term prediction and long-term prediction, and the evaluations are regarding the error, and the classification is also doing some significance tests in order to, if we claim that the model outperforms the other model, so at least it to be significantly, statistically significant. So here you see a short-term error estimation of each of the models. The upper table describes the descriptive statistics of each of the data sets, and the lower table, the yellow marks, say what model had the least error in each of the data sets. So you can see that the hybrid model had the lowest the lowest error in the packet loss, but each of the other models won in the different data set. But if you take a careful look, you will see that in each of the other data sets, the hybrid model was the third one in the frame delay. It was the runner-up in the jitter, and also the runner-up in the synthetic. So in terms of robustness, let me show you this table. If I collect this result, you can see that the hybrid model was the only one that it was in the top 3 all the time, at least in the top 3, of course, okay? If I draw this table, so in a metaphor, you can see that the more difficult to cross a wall from one side to other side for a given model, the more robust the model is. So here you see a visualization of the robustness of each models, and the hybrid models. The hybrid model is has the best robustness out of all the models. So this is for the short term. And if I summarize the short term comparison, so again, the classification results, we took some of the evaluation metrics of the classification, and we compared them all throughout all the data sets, and the hybrid model took nearly 87%. It won all the other models with 91 significance. So actually, it's nearly 80% of significant wins. And if I compare to the reactive mode, so it is much less. And the bottom table is a paired comparison between the hybrid model and the reactive, where you see the hybrid model outperforms the reactive. Now I'm going to switch to a long-term comparison. So here in this graph, instead of one table, so each point here represents a table that you saw in the short-term comparison. So you see that the exponential smoothing algorithm actually is very strong, and the hybrid model here is the runner-up. But when we compare the classification results, then we see that the more you go, the more forward steps ahead that you take, the longer prediction in terms of the term of the prediction. So the hybrid model is outperforming the rest of the models. And again, the robustness is decreasing a little bit, but is still, compared with the rest of the models, it maintains itself as the best robustness. So this is what we are after in terms of the model that we want to establish. So what we saw, I sum up the talk. We saw SDN and SDN applications, that it is very flexible, very dynamic, very easy to use. We saw the differences between being reactive and being proactive. We talked a little bit about the challenges of time series forecasting, and then I presented the hybrid model. And the results are actually very clear that it is indeed a very strong and robust model that was to apply. Just a quick note. Maybe I should have said it at the beginning, but this system, the one virtualization that you saw, is a system that, how much time do I have, Ori? 1 minute. Did I present Toga? I did not present Toga. So Toga, if you don't know, is a competence and innovation center for Huawei Technologies, a giant Chinese company. And this system is in production. If you have more questions about the one virtualization system, we have here Ofer Ben Yaakov, is a networking expert from Toga, and Charles Napiri. So you can contact us and offline ask some questions about the system, or also about the forecasting model. And regarding additional applications, also can be used for other applications, security, networking, and management. And that's it. Thank you.